Hey everybody, good evening. Welcome to week 4. I hope everybody's having a good night or morning or wherever you are. So the topic today is going to be UGens primarily. We're going to feast our ears on a whole bunch of UGens because we've been primarily doing oscillators, noise generators, and envelopes. And you can do a lot of stuff with that, but that's concretely in the territory of sort of plain old vanilla synthesis, and you can do a whole lot more with SuperCollider's UGen library. There are some, there's sort of a list of UGens. If we look up the UGen help file, you can see that there's a couple of links to other stuff. There's browse UGens, tour of UGens, and then there's I think primarily you want to go to browse UGens, and then you can see UGens divided into categories like delays, filters, generators, in and out, random, reverbs, etc. And then, for example, if you go into filters, there's linear, nonlinear, and the list just sort of keeps going. So we'll get into that. So yeah, UGen is going to be sort of the topic of the day. I did want to cover one thing though before we get into it, and it's something I didn't get to last time with if. So actually, first let me just make sure we have sound. Boot the server. So you should hear some pink noise. I certainly do. Yeah, you can look up tour of UGens. Here it is, and this walks you through some. I don't know if this is a comprehensive list, but it does have a bunch of code examples that you can just go through and play them and hear what things sound like. Okay, so let's talk about if. We have done a little bit with if. Let's say, for example, we were doing like rand 01 dot, no, just rand 01, right? Just make some random numbers. So we could say x equals, and then we say if x is greater than 0, then play a sine wave. Oops, I needed 2 there. Let's put a line on this. Done. Action 2. Let's open this up, why not? So I'm just cooking up a simple if then else. So if x happens to be greater than 0, do that. Otherwise, play a different sound. Play a sawtooth wave. We'll make this a bit of binaural beating, maybe 60 in the left, 61 in the right, and multiply that. Nope, multiply that by x line. Make it a little quieter because it's a little brighter. Yeah, so we have sine wave if x is greater than 0, sawtooth wave if not. Oops. And then we close out the if. And let's make this a one-liner here. So now if we run this, let's post ln, our number. Okay, so that's a 1, that's greater than 0, we get a sine wave. 0. Sawtooth. Sine, saw, etc. So this is all perfectly well and good. But it's only a matter of time till a new user tries to do if inside of a synthesis function. So let's do that. Var sig, actually, okay, so we'll do var sig arg choose equals 0. Var sig. If choose equals 0, then sig equals Sign osc. Is everybody there, by the way? How's everybody doing? Not a lot of activity in the chat. I want to make sure I'm not talking to myself here. Let's copy this. In some ways, yes, this program is like Sonic Pi. Sonic Pi is much more strongly oriented towards live coding. And sort of it's the whole environment. You're meant to play with it as it's making sound. SuperCollider, you can do a lot of things in non-real time. Okay, trying to keep up with typing. Yeah, well, you should try keeping up with typing on my tutorial videos. Those are edited to like 500% speed. Okay, so, getting back to, there we go. Okay, cool. Yeah, glad everyone's out there. So I'm just doing the same thing. We are going to set sig to a thing based on what the value of choose is. And then we'll say sig equals sig times 0.3, just scale it down a little bit, 2.2. I'm very indecisive with my numbers. And then that's it, because this is just a function.play. So we don't need out.ar, we don't need a name, we're being kind of sloppy. We will call this synth. Okay, so let's go ahead and play this. Oh, I meant to make this a sawtooth wave. Okay, so right away we can hear that we're getting a sawtooth wave, right? So this is the function being evaluated. So this must be false. But choose is equal to 0. So this is the first sort of question mark, you know, head scratcher. Choose is initially equal to 0, and we're testing whether choose is equal to 0, and that should be true. So we should get a sine wave, but instead we get a sawtooth wave. Okay, so that's one thing. Synth.set choose 1. Nothing. Choose 0. Choose 2. Choose 3. Choose -1. Choose minus a bajillion. Nothing's happening here. It's sort of stuck. So I tell you what, let's change our condition to be not equal. This exclamation equals combo syntax means not equals for anyone unfamiliar. So we're saying if choose is not equal to 0, do this. Otherwise do this. So let's play it. And now we have a sine wave, right? Sine wave, plain and simple. Oops. That's not working either. What is going on? Okay, so you know what? Let's actually, why don't we even poll our choose, right? So this is going to declare our argument, declare our variable, poll the value choose. Poll is like post-ln, but it works on the server instead of the language. So we'll just run this. And we can see our UGen output proxy, whatever that is. And we can set this to a value of 1. And it's changing. It's definitely changing, but nothing is going on here. And just for posterity, let's make this a synth def. If out.ar. So now we're making this into a synth def, and instead of playing it, we're going to add it. Bang, there we go. We have a synth def called if, and now we'll say synth equals synth.new if synth.set. Okay, so initially we should, let's even set this equal to 0, right? It's the default is 0, but we're being extra certain that it's 0. Okay, nothing. It's not working. So this is a common thing to run into, especially if you're kind of new and you've learned what if is and you've learned what synth-def is. It's only natural to try to put branching conditional logic in a synth-def. And you will find that it does not work. And I'm now going to try to explain why it doesn't work. And it has to do with the separation between language side and server side. If is a language side operation. The way it works, where it lives, it's all language side. And when we make a synth-def or play a function or do something which involves taking a function of unit generators and passing it over to the server, the first thing that happens is that the language goes through it and it evaluates everything. It basically, if there's anything, like language side, like if we say 2 + 3 dot post ln, and if we add this, we do in fact see like all the language side stuff happens, right? And if is a language side operation. And once this moves over to the server, it's out of the realm of the language. So the language goes through, the interpreter says, okay, if choose is not equal to 0. And well, let's go back to our first example where we said choose equals 0. And we would expect to get a sine wave, but we get a sawtooth wave. So there's two problems going on here. First of all, well, okay, to better illustrate this, let's do this, right? If choose is greater than 0, all right, not equal to, not equal to, greater than 0, and we get an error message in this case. So that may have been not something you were expecting. So error, non-Boolean in test. This is the kind of error you get if you do something like 1 greater than hello. Oh, okay, that didn't work. There's something. What can you not compare? An array, maybe? You can compare everything. 1 greater than rect.new. Yeah, okay, that doesn't work. Non-message greater than not understood. So that's a similar message. The thing going on here is that choose is not a number. It's not an integer. It's not a float. Let's actually post ln choose. So it looks like we're saying choose is the number 0. It certainly looks like we're doing that. But the server is a complicated beast, and when we pass a synth-def over to it, it does a whole bunch of magic. So let's see what this returns. Okay, it's still getting non-Boolean. Let's change that to that. Yeah, so here is our post ln from choose. Choose is an instance of a class called output proxy. So that's not a number. So when we do something like equals, this is not, even though the default is 0, we're asking whether an output proxy is equal to 0, and that's false. So that's why we get a saw. So that's why we had this strange thing. Choose is not a number. That's item number 1. The other thing is that the language, when it's asked to interpret a synth-def and then add it to the server, it goes through this if once before compiling and sending to the server. It says, is this true? And if it's true, sig is set equal to sign osc. Period. End of story. Add. Go to the server. I'm done. Right? If this is not true, sig is equal to saw. Period. End of story. Go to the server. I'm done. So this logic is not updated on the server, on the audio server. It's not, the server doesn't, it just sees this as a static value, right? This is equal to saw, whichever of these two functions gets evaluated. So if this is false, the server only sees this. That's what the server sees. So yeah, that's why if doesn't work. So you might be thinking, whoa, so I can't use conditional logic on the server? What a useless programming language. It is done, maybe sort of for optimization. It's really more a design choice than anything else. Here's the thing. You can do conditional branching on the server, but you just have to speak the server's language. The server really only understands one type of data, floating point numbers. And that's what all these UGens actually output when they're running on the server. Okay, so let's say we actually want to do this thing where we check, and be able to change what sig is equal to based on some condition. And this is actually a pretty good segue into the rest of the lecture tonight, which is new UGens. So there is a UGen called select. And because we're going to select between two audio rate things, select is going to be an audio rate unit generator. And we're going to set sig equal to select. Okay, so sig is equal to select. Select needs two things, which and array. Okay, that's not very meaningful, so let's look up the help file Right, select. The output is selected from an array of inputs. The first argument is an integer index, which is going to be used to address the corresponding item in an array. So our first argument is choose, comma, and then an array containing UGens. So we'll do this, comma, and this, close the array, close the select, and delete all this stuff. This is the simplest way to translate language-side conditional logic using if to server-side conditional logic. So let's add this. We've overwritten our old broken syntef called if with a new syntef with the same name. And now we're going to start with choose being equal to 0, which means the output of select is going to be the item in the array at index 0. That's our sine wave. And now we can change choose. And we can do something like ran 0, 1, post ln. There we go. Alternatively, we can do the array 0, 1 dot choose dot post ln. And this is sort of cute. We can do 0.5 dot coin, and this returns true or false. Actually, it's not going to work because we need numbers here. So this is a way to get trues and falses, but probably the best way to do it is just, yeah, okay, synth.free. So that's sort of a quick solution, is using select. The downside of using select is sort of what Pierre said about optimization. Both of these UGens are running simultaneously. It's just that select is muting all the other ones and only allowing, it's like a gate basically. When you get an index, it just sets all the other UGens to 0, or just zeros them out. So they're all running simultaneously. So if you have like a select and you want to choose from like 200 different UGens, you know, you can, but they're all running simultaneously, so it will sort of add up after a while. So that's if in the context of the server, just to use something called select. So give me a sign. You with me? Because I think we're going to move on to some tasty UGens. So let me know how everybody's doing. Got it. Love it. Okay. So up first, in addition to select, cool, thank you, Schweidi. I want to talk about the MUS UGens, and they are MUS X, MUS Y, and MUS Z? No, not Z. We don't know if we're moving the mouse up and down. It doesn't make any sense. It is mouse button. So MUS X, cursor tracking UGen. We provide MUS X with a minimum value and a maximum value, and it will translate the MUS X position into a value in that range. MUS Y, self-explanatory with MUS X, and MUS button is basically outputs the maximum value when pressed and the minimum value when not pressed. So let's just put one of these into use. Let's see, let's do the most ultra basic thing we can possibly do. So in the past, we've been saying, you know, frequency is some noise generator or some sawtooth, low frequency sawtooth wave or this or that, or an envelope. But here we're going to say freq is MUS X. And we're going to go from 100 to 3 million. No. We'll go all the way up to 15,000. And warp, I only use 2 values here. 0 is linear, just like envelope curvatures, and 1 is exponential, I think. Let's go back to, is that right? Yeah, 0 is linear, 1 is exponential. So let's also poll this because it's fun to see what value we have. And then signosc.ar freak 0, not too loud. We can do exclam too there. Dot play. So 100. Okay, that's, you know, I thought about it, I was like, that's gonna sound bad, and it does. I don't like that. So there we go. Just up to 2,000, down to 100. And exponential is gonna give us the most natural sort of sound because each time we move the Schweides in disbelief. No way. So with exponential, with this 1 here, every time we move the same distance, the frequency increases by the same ratio. So like that's each linear distance corresponds to the same musical interval. So I'm being really sloppy, but if we do linear, then the second half of the screen is an entire octave from like 1,000 approximately to 2,000. So we're going to be sort of in totally high territory here. So they're slightly different. I prefer exponential for frequency. Okay, so let's add amplitude. And this is going to be mousey.kr. We'll go from 0 to 1 linearly. And we'll pull that as well. And we'll just multiply this by amp. So we've got our new variable, amp. It's going to be, I think it's 1 up here and 0 down here. And I actually have 2 monitors right now. I have all my crazy stuff down here. And the mouse Y and mouse X, they respect these boundaries on the primary display. But if you go off onto your other display, it'll just keep going in that direction. So I'm actually going to clip these between 0 and 1. Not that a negative amplitude is going to do anything bad. It's just going to invert the signal, but I still am going to clip them just so in case I drop down onto my second monitor, we just stay at 0. So yeah, so I'm at the bottom of the screen. And we have the classic SuperCollider theremin. I'm a digital Clara Rockmore, check me out. Except I'm way, way worse than her. So if I go down onto my monitor here, my mouse is on my second screen. See, here's my window, down it goes, and we just stay at 0. So yeah, if you ever have 2 displays, you want to clip these values just to be extra safe. So, okay, so mouse button. The simplest thing we can do with mouse button is to just use it to turn the sound on and off. So we can just have a second amplitude variable and set that equal to mouse button.kr. You definitely can hook this up to a MIDI controller. That is one of our topics, like sort of right around the midterm. There's a whole family of MIDI classes. SuperCollider is 100% MIDI compliant, and you can receive data from MIDI controller and then map that. You can make a note on start a synth. You can make a note off free a synth. It's all relatively simple to do. Okay, so mouse button, min val. This is when the mouse is not pressed, and this is the value when the mouse is pressed. And I think that's it, right? Mouse button. Yes, you have a programming midterm. It's on the syllabus. It's not going to be hard. It's just going to be like an in-class, maybe 3-question affair with 2 easy questions and 1 medium difficulty question. Oh yeah, lag. Lag is an interesting thing. Let's just go with no lag right now. Lag is simply a sort of a thing which causes the signal to become sluggish and actually sort of fade from 0 to 1 and 1 to 0. Okay, so then we're just going to multiply this again by amp2. So if I play this, we should hear nothing because I'm not pressing the mouse. And now I'm going to click with the mouse and hold the mouse button down. Here we go. Click, release, click, release, click, release. Of course, I'm also dragging my text around while I do this. Okay, now I've gone and messed it all up. Let's undo. Yeah. Okay, so you see, all very fun. And all you need to do is just determine what suitable minimum and maximum values are for the mouse button that you want to play with, and then put those in. Right? For mouse X and mouse Y, this is the left and right, or bottom and top of the screen. And this is just what value to produce when the mouse is not being pressed and when the mouse is being pressed. So for example, you would not want to put 102,000 and then plug this in for amplitude, because then you would be, as we know, a value of 1 is really the highest amplitude you want. 2 is twice as loud, probably going to clip. So 102,000 are absolutely terrible values for that. So that's mouse Y, mouse button, mouse X. Very fun. Good for testing stuff too. Like if you, I did this once. I did like an installation at the University of Texas where we clamped, my collaborators and I clamped subwoofers and contact mics onto handrails. And then in order to find the resonant frequencies that caused the systems to feed back, I just sent a sine wave out and used the mouse to sweep through the entire spectrum, and so that I could find the fundamental of each segment of metal handrail and all the harmonics, and I would just write those down on a piece of paper, and I used Pole to print those values. It was really very satisfying to be able to just move a mouse and have the whole building sort of just come into resonance. It's really cool. Anyway, so those are the mouse buttons. Let's move on. Big topic here, buffers, okay? So buffers, let's look at the help file for buffer. What is a buffer? There's actually, this is a long help file. There's a lot of stuff going on here. As I mentioned at the beginning, we've been doing synthesis, right? Sine waves, triangle waves, sawtooth waves, pink noise, white noise, envelopes, usual. But we haven't done anything with recorded sound. So buffer is your access point into recorded sound, but buffers also do a whole lot more than just dealing with recorded sound. So description, a buffer is most often used to hold sampled audio, such as a sound file loaded into memory, but can do a whole bunch of other stuff. Buffers are commonly associated with PlayBuf, RecordBuf, disk in, disk out, BufWrite, and BufRead. We're going to talk about PlayBuf and BufRd. And yeah, buffers have a number of attributes. They're very flexible objects. Really, the 99% of the time I'm using buffers, I'm reading a sound file into SuperCollider from my hard drive. So let's do exactly that. B equals buffer dot, wait for it, read. Buffer dot read. That's what we want. Buffer dot read takes a number of arguments. The first is the server on which we want to read the buffer. And this is the localhost server S. You can also use buses for so much stuff. That's true. I don't know if you're talking about buffers or buses, but they are both very useful. We're going to get into buses next week, I think. So we're going to read this buffer onto the audio server, our local server. It's possible to read a buffer onto somebody else's server somewhere if you're doing networked audio. But the first argument, 99.9% of the time, is just going to be S. We're going to read this file onto our own server. And then a path to the sound file. A string representing the path of the sound file to be read. Now, yes, you can go, let's go sounds, SC audio. Here's my wacky sound library. There's probably some embarrassing stuff in here. I'm going to go into a folder called Grow, which is the last name of a percussionist, that Adam Grow, that I worked with, and we did a recording session for a piece. And I have a whole bunch of percussion sounds. So let's get this metal pipe and this one. Now, what you can say, okay, well, you know, get info, and you know, we got to figure, okay, where's the path, name and extension. You know, it's just a real drag. And then one day I realized you can just do this: click, drag, drop, kablamo. That saves you a lot of time. So here is the full path to the sound file. And something I do want to cover today is the dilemma of submitting an assignment with sound files on your own computer, and I don't actually have them. So there is a way to make this sort of very mobile. It's sort of one little directory that you can just zip into a zip file and send that, and all the resources go with it. So, okay, so this is all we need. There are other arguments like start frame, number of frames, action, and buffnum. Start frame is basically the starting sample that you want to read. 0 would be the beginning. So you could start at sample number or frame number 100 and skip the first, you don't, and then -1 means read the whole thing. You can only, read just 1,000 samples or so, but the default is -1. So by default, we're going to read the entire sample into memory. And we're not going to worry about action and buffnum for now. I just want to say that buffnum is an integer that is automatically associated with this instance of the buffer class, and that's how we then refer to it. We say what's how long is buffer with buffnum 6? How many samples is buffnum 9? Even though we are calling it B, this is how we refer to it in the language. So okay, enough with the chatter. So we're just going to run this line. Okay, and then start frame is desired time in start frame. No, start frame is basically starting sample. Okay, so I'll answer your question by continuing here. First of all, just to confirm that this has loaded correctly. Oh, good. Do you want to hear that? Yeah. It's kind of quiet, but this is what I usually do if I'm loading a buffer, just to make sure that nothing weird happened. We can let me open up this file just so we can have it, open in Audacity or something. Yeah, so here's our file. That's not playing on stream, I know, but just to sort of look at it, we can see that it is a monophonic file. It's just one channel. It's about 8.35 seconds long. Okay, so let's hide that. And let's we can ask cool, thank you, Pierre. We can ask things like b.duration. Oh, I nailed it. Look at that. 8.359. That's the length of the buffer in seconds. We can say b.num frames. This is 368640. So there are 368,640 frames in this buffer. Frames are a lot like samples, but they are not quite the same thing. I'll get to that in just a second. b.num channels. This is important. 1. So buffers are pretty much, sound files on your computer generally are going to be 1 or 2 channels. So this is monophonic. It's just got 1 channel. It's important to know how many channels your buffer is, because PlayBuf and BufRd and these UGens need to know how many channels, because you can't modulate the number of channels. You can't suddenly expand the number of UGens in an array. That's something that has to be fixed. So, okay, so duration, num frames, b.sample rate. This was recorded at a sampling rate of 44,100. Usually you want this to match s.sample. Sample rate. And they do match. If they don't, it's not a disaster. You can do all sorts of stuff to fix that. Okay. So let me just briefly talk about samples and frames. I think it's up here. Okay, so multi-channel buffers interleave their data, thus the actual number of available values when requesting. Yeah, so the number of samples is equal to the number of frames times the number of channels. So since this is a monophonic buffer, there's only 1 channel. So therefore, the number of frames is equal to the number of samples in the buffer. But if we had a stereo audio file, and if we read that in, I might try to find a stereo file, actually. Maybe one of my piano samples. Is that stereo? Yes, it is. Okay, so C equals buffer.read S, and we'll just pop this in here. And so C.num num channels, that's 2. So in this case, the number of samples is twice the number of frames. You can think of a buffer as, it's the number of channels horizontally, and then it's sort of divided into samples this way. And a frame is sort of a vertical slice. So if it's a 2-channel buffer, you have 2 samples in one frame, 2 samples in the next frame, next, and 2 channels. So if you had a 4-channel audio file, one frame would consist of 4 samples. It's a subtle concept that you don't really have to deal with too much, but anyway, let's see what this one sounds like. Yeah, it's like a piano reverberance thing. Okay, so that's the first step of using buffers, is just reading it in. Now, in some cases, you might want to, you have a sound, but you just want to read one channel in. A lot of granular unit generators, like UGens that do granular synthesis, they need a monophonic buffer in order to work. So the way we do that is with, well, first of all, let's do c.free. That reallocates that buffer. It's sort of a good thing to do. Buffer.read, not read, but read channel. Let's look this up. Buffer.read channel. So server, path, and then a bunch of the same stuff. But then there is an argument called channels, which is an array of channels to be read. Indices start from 0. So this means you can read any sort of custom number of samples. But typically, what we end up doing is we have some stereo file, and we want to skip to the channels argument and just say only read the left or only read the right. So let's just do only the left channel. There we go. And now if we c.play, if you're on headphones, you'll only hear this in the left because C is now a 1-channel buffer, just like B. Okay. So let's c.free and read in our original stereo buffer. So now we have 2 buffers to play with, B and C. The array b comma c dot do argbuff buff.play. There you go, a little bit of iteration for you. Okay, but let's get into UGens, and we're going to start with PlayBuf. PlayBuf. I use PlayBuf so much. It's so simple to use. It's probably the fastest way to just get a sound file to play. Playbuff.ar, we're going to play this sound, so we need audio rate. PlayBuf expects the number of channels of the buffer. The architecture of the synth cannot change after it is compiled, so this is a fixed integer. So in a lot of cases, you might have one synth that plays mono buffers and another synth that plays stereo buffers, because you really can't use one for buffers of different number of channels. So we'll make this one channel, and then the buff num. And we could say, b.buffnum, which happens to have a buff number of 0, surprise, surprise, because it's the first thing we read onto the server. But here we're basically hard coding in the value 0, which means this function will only ever be able to play one buffer. So the right thing to do is to make an argument for the buff num, and maybe initialize it at the beginning. Let's make we'll keep this as a function for now. Okay, rate. Third argument of PlayBuf is rate. This is a playback ratio, where 1 will cause the buffer to play back at the its original rate as it was recorded. 2 is twice as fast. 0.5 is twice as slow. And this is like tape speed variation on old tape decks, where if you double the speed, not only do you cut the duration in half, but you also shift the pitch up by an octave. So we'll say rate, and we'll initialize rate to a value of 1. Trigger. We learned about triggers a little bit, I think. Remember we had this t argument, t underscore. This is basically a value which will cause PlayBuf to jump to its start position. So this is good because you can send a trigger and set the start position to like 0, right? And then whenever the trigger argument gets a value of 1, PlayBuf is going to just jump back to the beginning, wherever it is, and start from the beginning. So we'll also say spause for start position. So this is our t trig and spause. And then there's a loop argument. This is whether it'd be a good thing to use select to figure out using a function the number of I guess that could work. You could have one PlayBuf with one and another PlayBuf with the other. Actually, yeah, that would work. Yeah, it's a good idea. It just means they're both running simultaneously. But that's, I mean, they're just indexing into a array, so that's all a sound file is on the server, by the way. It's just an array of floating point numbers representing the sample values. So in the language, we have arrays with square brackets that contain stuff. On the server, a buffer is an array. It just so happens that the only type of data in the array is floating point numbers. Okay, so then loop. We'll set the start position to 0. Remember, the array indices start at 0. And loop will initially say 0. 0 means don't loop. 1 means loop. And guess what? PlayBuf is a finite UGen, just like xline and line and envgen, which means it has a done action. And basically, whenever PlayBuf gets to the end of the sound file, and if loop is 0, meaning it's not going to loop, it checks its done action. And if done action is 2, the whole synth just goes away. So let's say done action 2. Keep in mind, you can make an argument for done action. You know, you can modulate done action. That's totally legal. So there we go. We're gonna say sig equals. Now this sound file was actually kind of quiet. I think the peak amplitude is, yeah, like 0.5. So I think we can actually double the amplitude without clipping. And we'll make it stereo. This is just mono, right? A mono file. So we're gonna make it stereo. We're just gonna copy that from one channel to the other. Let's see if I did anything weird. Yeah. And let's bring up our node tree. And remember, this sound file is 8.35 seconds long, so some of them are getting to the end. Boom, boom, boom. Right. Let's say, let's make this a synth diff real quick. Play out.ar 0 sig exclam 2. Okay, so now we have ourselves a synth diff. And we're going to say synth dot new play loop 1. And maybe I should have picked a shorter file, but that's okay. Once we get to the end of 8.35 seconds, notice that even though done action is 2 and PlayBuf got to the end, it did not free itself, because when loop is, doesn't it say that here? Oh yeah, done action is only evaluated if loop is 0, and right now it's 1. So, oh, you know what? I didn't give this a name. Let's call it x. There we go. We're going to say x.set rate 2. So now it's about 4.17 seconds long, and it's looping. Yeah, we're getting a little crazy here. Okay. Normally, loop doesn't go that high. I mean, you can. It just starts to sound crappy. Let me get a new file in here. I think I have like a short something we can use. Where's my percussion library? Something you can do if you ever feel like it is just buffer.free all. Just deletes all the buffers, reallocates all that memory. Let's do a shaker. Maracas 3. So I want this. I'm going to copy that, and we're going to put it here. So now B is little bit of maracas. So might as well get these level meters up here. So now just to be, what we should be doing is we should also be saying which buffer we want to use, because buff b.buffnum. This is how we tell the synthef which buffer to use. Yeah. Oh, maybe I shouldn't be multiplying by 2 here. There we go. So now if we say rate 2, right? 1 octave higher, twice as fast. Yeah. Okay, so that's rate. If we do x.set t_1, we have the ability to cause PlayBuf to jump back to the beginning. And we could also change the start position to be somewhere in the middle of the buffer, and we could jump. Start position is a value in frames. So, we could say x.set spos. Let's just estimate 4,000 frames. So now if we trigger it, let's go back a little bit. Let's see. So now the initial attack of the maracas is actually over within 3,000, samples. So now we're actually kind of jumping back to a part as the maracas are kind of decaying. Okay. But we're not really getting into the totally fun stuff. So let me just let's get another sound file. As you can imagine, you run out of lowercase letters pretty quickly when you use them for buffers. So you might want to, use tilde variables or something. And also you can use an array to bring a bunch of buffers into an array. Maybe that'll be like a question on one of the take-home things. So what am I doing? Buffer UGen, no buffer data when trying to make the synth. If you paste bin your code to me, I might be able to help you. It's a little hard to figure it out without it. Okay, so I want to get something relatively short. Now what do I want here? I just should have planned ahead with like a sound file. I want to do something sort of sustained but pitched. So okay, flower pot sustain. This is a nice sound. I'm into this one. Let's do C, and we'll drop this into C. Okay. So now I'm gonna change this synthef. I'm gonna make a new one. I'm gonna call it play2. So separate synthef, and we'll leave it alone for now. Actually, I just want to keep things simple here. No, it's fine. It's fine as is. I don't even need a new one. We'll keep it anyway. So now we just do x equals synth.new play2 buff c. Right, we've got our argument called buff. Yeah, let me take a look at this paste bin real quick. And we'll come right back to this. So this all looks fine. Just make sure here in you want to, presumably somewhere up top you loaded some buffer with a path that makes sense on your own computer, s comma string representing the path. Run that file, and then here you want to do buff c, I guess c.buffnum. Yeah. And also what you can try is just whatever you named your buffer as, just do that dot play and make sure sound comes out. I'm gonna turn up the sound on OBS a little bit. Okay. So, yeah, no problem. Don't save that. I just want to demonstrate that, a lot of stuff we were doing with synthesis, we were plugging like a triangle wave into the frequency of a sine wave, or a low frequency sawtooth wave or noise generator into the amplitude of some other thing. And you can do that exactly the same with PlayBuf, and it's really, really cool. So let's do, let's make an amplitude argument. Let's make it equal to 1. Here we'll say amp 2.5. Let's see how this sounds. Okay. So let's say loop 1 and so we're gonna modulate something with so instead of a fixed number for rate, of course we can modulate it, right? We can say x.set rate 2. Oh, and if you ever want to do like semitones, like if you want to play this buffer like it's on piano keys, what ratio do you do for a half step, right? Is it like 1.16 something? That's not it. Right, you kind of have to guess, and that's stupid. But you don't have to do that using the MIDI ratio method. MIDI ratio takes a transposition value in semitones, where a semitone is 1, an octave is 12, a perfect fifth is 7, and it converts that into the appropriate ratio. So watch this. So 0.MIDI ratio returns 1, because 0 means no transposition, so we're sticking with the same note, and that just has a ratio of 1 to 1 with itself. So here's 1. I can do math. Okay, so that is MIDI ratio. That is mega handy, and you should memorize it. I use it quite a lot. Let's switch things up a little bit. And instead of rate as an argument, let's make rate a variable. And we'll set it equal to a sine wave, which has a frequency of 0.5 and a range between 1 and 1.2. Okay, so you ready? Our rate is now controlled by a sine wave, and it's going from 1 to 1.2 over the course of 2. It's going 1 to 1.2 and back, a full cycle every 2 seconds. So now it sounds like this. And we can do something like max transpose. That's kind of a long name. Let's do max turnsp. And we'll say max turnsp equals 1.2. Okay, and here's something cool. Let's, for a moment, just set this back to 1. So now it's just stuck at a value of 1. Or let's bring it back here as an argument. What did I do wrong? Oh, it can't be declared as an argument and a variable. That's why. Okay, so what happens if we go all the way down to 0? What happens is playback is frozen, right? The playbuff is just sitting at a sample and its rate is 0. So we're just outputting some constant DC voltage. So what do you suppose happens if we do this? Rate -1. Yeah. We just have, like, if we were to look at the scope right now, we just see some, you know, it's just outputting some constant non-zero value in the buffer. So, you know, it's probably not a good thing. But watch what happens when we do rate -1. It goes backwards. Backwards it goes. Okay, so that's rate. You can go forwards, you can go backwards. The only thing you want to be careful of is if you are not looping and you go backwards, what happens is, as we go backwards, we wrap back around to the end, and whenever the current sample is the last sample, and if loop is 0, that's when PlayBuf checks its done action. And if done action is 2, it frees the synth. So actually, if we try to go backwards, starting at sample 0, the very next sample is the last one. And so, wait a minute. I'm confused. Oh, there's no comma here, so it's not actually setting it. Okay, so yeah, I forgot to put a comma after rate, so I don't really know what it was doing. Probably rate was just defaulting to its value of 1. Yeah, so notice how this does not work. Nothing even shows up in the node tree. So that's because we're immediately going backwards from the beginning, going to the end, and then done action 2 is saying, I'm done. Okay, I want to get to BufRd. This is an alternative to PlayBuf. Now, PlayBuf is sort of automatic, because you give it a rate value and it just runs, right? You can change the rate and the speed will change, but it's sort of always running. BufRd is a little bit different. If I can get my bearings here. Let's make some room. Synth, def, new, play, 3. Very, very bad names. Okay, so we're obviously going to need some buffer to play. And var sig equals BufRd.ar. So BufRd is quite different in design in comparison to PlayBuf. PlayBuf plays through the buffer by itself. BufRd only moves its read point by the phase input. That's the third argument here, and therefore has no pitch input. So BufRd, we give it the number of channels, which, what is that? What were we using? B? C. .num, just to remind myself. I think it's 1 channel. Yeah, 1. And then we want to do c.buffnum. That's the second argument. Which buffer are we reading? And then phase. So I'm going to just say phase for now and close that out, and we'll make a new argument here. So phase needs to be some audio rate unit generator that will be used as an index into BufRd. And this is just a raw sample index. So c.num frames, the value of phase needs to be between 0 and this value -1. Because indices start at 1. We have this many frames, so the last one is 990.207. So let's start with just a simple line, .ar, going from 0. And yes, we can paste this in here. This is not the right thing to do. We're going to do it temporarily. Duration, well, we can say c dot duration 22.45. We'll just copy this value. This is not the right way to do it, but I just want to give you guys a sense of what's going on here. And then we'll use done action 2 to stop it. So what this line should do, we need an out. What this line should do, we're going to multiply this by 3.5 like we did before, is just go from 0 to this value. Oh, that should be a 7 over this many seconds. Very, very accurate value. And it's going to be used as an index into this buffer using BufRd. So we should just be able to do synth.new play 3 argbuff c.buffnum. You get the idea, right? It's going straight through, and maybe I should have let that play, but this is a dumb thing to do, putting these numbers in here, because if you suddenly provide, you know, a different buffer for the buff, you know, argument, so this BufRd is reading into a different buffer, these numbers are not really related, right? So we want to be able to adapt, and the way to do that is to use the Buffer UGens. So there's a whole bunch of Buffer UGens. There's something called buff frames, gets the current number of allocated frames. And here's one of the rare cases where it makes sense, sort of, to use IR, because we really only need to check the number of frames in a buffer once, because it's not going to change, right? I mean, we could switch to a different buffer, and in that case, we would want this to be running at the control rate, so it's constantly checking. But let's go with IR for now. That's probably fine. And here, we want to know BufDur gets the current duration of a sound file, .ir buff. And if we poll these, we should see what have I done? Oh, a different buffer. That's what I want. C.buffnum. And that didn't work because I forgot a square bracket. Yeah, so just stop that for a second. We can see that as we're polling buff frames, we're getting this value. We should probably do buff frames -1. Right. We're getting 990207, that's the number of frames, and the duration, 22.45, etc. Okay, so that's line. Let's do X line, and we'll start at sample number 1. Wait for it. Maybe. Here it comes, here it comes. Okay. Yeah, so we've just read through the buffer using an exponential line instead of an AR is sample rate, KR at each block. IR is short for initialization rate. UGens that have an IR are evaluated exactly once at runtime, and they are never checked again. So whatever their first value is, that's their value forever. So yeah, that's IR. Poll prints the value of a unit generator. So here's a sine wave dot poll, and we don't actually want to hear that, so we're going to end with a 0. And now we're just watching the values of the sine wave. Right, so, and poll by default, I think, checks 10 times a second. But you can say, yeah, 10 times, you can say 50 times a second, and then you get a whole lot more numbers. It's like post ln, but it's for the server. Because if you do post ln here, what you get is the language side result. Oh, it's a sine os. Well, it's like, okay, that's not what I wanted to know. I want to know what its values are. And so that's what poll is useful for. Poll actually checks, it queries the UGen, says, what's your current value? What's your current value? What's your current value? And it does that 10 times a second, but you can tell it to do it a lot more. It's an expensive thing to do. Oh, now I've done it. Oh, yeah. Okay. Come on, you can do it. Oh, please. Maybe this will do it. Come on, where are you? Get those. Gosh, it's not good. Quit. Did that work? Yes, I think it did. Maybe. Yes. Okay. Don't do what I just did. Yeah, poll should just be used. It should stick with the the default 10 times a second, because if you, I mean, poll actually results in the production of a unit generator called poll. And it probably says somewhere in the help file. There it is. Yeah, warning. Printing values from the server is intensive for the CPU. Poll should be used for debugging purposes. So, my bad. Let's pick up where we left off with okay, so that's poll. Oh, it's nice that it makes auto backups. I thought I was gone for sure. Okay, so the last thing I want to do with BufRd is that you don't have to use a start to finish sort of thing. You can use a low frequency sawtooth wave that goes from 0 to, let's say, well, you don't have to say that. We could say buff frames.ir divided by 10. So only a, no, I'm sorry. I'm doing this totally wrong. I'm thinking of it like it's a line. LFSaw is an oscillator, and we need to provide the frequency. And what we can do is the inverse of the buffer duration. Right? Because frequency and period are inversely related. So this will give us a frequency which is consistent with the duration. So it'll play, this is the normal rate. And then we want to say range 0 to buff frames.ir buff -1. And what is your problem exactly? Let's say buff. Oh, you know why? It's because I crashed and I lost all my stuff. So there we go. I needed to reload my buffer. Yeah, that's what we need. So now, oh, okay, this is important. The third argument for BufRd, the phase, needs to be an audio rate modulatable index. So this is KR, so that's not going to fly. So we need AR. Now that'll work. Okay, so this is a sawtooth wave. It's going. Yeah, buff_door would dot reciprocal would also work. All right, that you can also do dot reciprocal. And then, you know, we can multiply this by 2, and then the frequency is twice as fast. And now we can think of this like a typical rate argument, right? So there's this. This is kind of on multiple lines here. I know it's not the most legible thing. Maybe we can separate this out a little bit. So if we say rate is 1. Right, and because this is a sawtooth wave, it is an oscillator. So it goes from 0 to, beginning to end, beginning to end, beginning to end. So let's do something fun here. Let's do a sine osc. And we're going to go from 0 to sample rate times 2. So s.sample rate times 2 gives us a value of 88,200, and this corresponds to 2 seconds worth of audio, right? So the sample rate is number of samples per second, so twice that many samples is 2 seconds. Very simple. And yeah, let's keep the rest of it the same, I guess. Let's make the rate 10. So what's happening here is the sine wave is going from the, sample, the beginning of, to the sinusoidally to 2 seconds into the file, and then it's going backwards to 0 sinusoidally, and it's sort of sinusoidally oscillating through the buffer from sample number 0 to sample number 88,200. Let's do an LF triangle. Now this is going to just go linearly. Forward, backward, forward, backward. And you can mess around with all sorts of UGens here. Okay. That's kind of a sloppy introduction here. If we want to get through a lot more UGens, we got to sort of make sacrifices here, but I love questions. So if any of this is, if you have questions, and I have a tutorial on buffers, tutorial number 8. So that's a good one to watch. It's a 28, 30 minutes or so of nonstop buffers. A lot of the same stuff I'm covering here, but I do it a little bit more methodically in that tutorial. So please, especially my students, go out and watch tutorial 8 at some point. I think it'll probably help you a lot. So moving on to filters. Filters are great fun. Who doesn't love a good filter? If we go to Browse, UGens, if we go to Filters, at the top there's Linear. I know that sounds boring, but it's actually where most of the really useful stuff is. And most lectures on filters will typically break filters down into 4 categories: low pass, high pass, band pass, and band reject. And those are LPF, low pass filter, HPF, high pass filter, and then BPF, band pass filter, and BRF, band reject filter. And those, nothing could be simpler to use. So let's do, let's just keep things simple and do pink noise. Good old pink noise. Who doesn't love pink noise? So sig equals lpf.ar. So LPF is a second order Butterworth low pass filter, and it needs an input signal, a frequency, which is a cutoff frequency. Everything below the frequency will be more or less allowed to pass through the filter because it is a low pass filter, and everything above will be, attenuated. And the higher it is above the cutoff frequency, the more attenuation it gets. We might as well do, so let's fill this in. Sig LPF, low pass, or maybe just even shorter, cutoff frequency. CF, arg CF equals 1,000. And let's give this a name. And let's freak scope it up. New. This is a useful tool. I'm going to nudge this stuff over here. Drop this right up here. You know what? Let's have some luxury here. This here. We can see everything here. Okay, so there we go. Let's just start with 2,000. And a very logical thing to do might be, let's comment this out, cf equals mousex.kr. Let's go 20 to 20,000, exponentially clip between 20 and 20,000 to be safe, dot poll. Okay, so there's our low pass filter. If we change this to a high pass filter, then it's going to allow things above the cutoff frequency to pass. Okay, now, before we go any further, I just want to make it very clear that filters are dangerous. Filters are dangerous. Filters divide into two categories: finite impulse response and infinite impulse response. And infinite impulse response filters, which is HPF, LPF, and a lot of the other ones we'll be working with, incorporate their output into their input in determining how to process future samples. So they involve feedback. And the cutoff frequency is basically an input to the transfer function or the equation that involves these mathematics to feed the output back into the input in order to affect. This creates resonances and all sorts of cool things that are so great about filters. But in SuperCollider, there is nothing, I repeat, nothing preventing you from putting in bogus values into a filter and causing it to explode. And if you are just being sloppy and careless and you have your headphones on and your volume's all the way up and you put a negative number into your cutoff frequency, oh, you're going to be so sad. You're going to, oh, it's going to be bad. So what I'm going to do, I don't like to do this. I kind of do, but officially I don't really like to. I just want to show you what it looks like on the frequency analyzer and on the scope, because this is fun. It's fun. Who doesn't like a little explosive filter action now and then? What I'm going to do is I'm going to mute the audio for myself and I'm going to mute it for you. So the first thing I want to do is I'm going to play the sound and then I'm going to mute on off OBS. And I just want you to confirm in chat that it is in fact muting so that I don't damage anyone's ears. So now I'm going to mute this. So off, on, off, on. So somebody please let me know if that was actually muting the sound or not for you. Muting, yes? Confirmed? Okay, good. So I'm going to play this. And now it's muted for you and it's muted for me. Now what we're going to do here is we're going to say, let's go from 5,000 down to, let's be dummies here and go -300. Okay, and we have to go linearly. We can't do exponentially because we're crossing 0. So we're going to see cutoff values here. And as I move the mouse to the left, we're going to get close to 0, and then we're going to go into negative territory. And I tried this before with the low pass filter, so that's what we're going to do here. So you should hear no sound. If you do hear sound, just mute your computers right now. This is going to be really bad. So we're going left. You can see in the corner, values are dropping. Everything seems normal. Nothing to see here. Everything's normal. We're getting low. We're getting low. And, oh, torture device. Yeah. You don't want to know what this sounds like. Yeah. It's not great. Okay. So, let's stop that. And so I'm turning the sound back on. It should be sound now. Okay, so filters are dangerous. You should, it's like a lit match, really. It's because it's normal to do stuff like sine osc dot exp range, something like 200 to 3000, and this is maybe we'll mouse x kr this guy here 1 to 10 exponentially. And maybe we'll change this to a saw.ar 60, 61, 0.2, 0.2. But these are all perfectly acceptable values, but there are a number of situations which are a little bit subtle, which, you may not realize it by looking at your code, that, your values for your cutoff frequency or your quality, which we'll get to in just a second, they drop into the negatives or something. Also, if you go too high, bad things can happen, but usually it's negative values for cutoff frequencies that go kaboom. Okay, so I am glad that I didn't harm anyone in the making of those sounds. So let's do a bandpass filter right quick. Let's bring this back to a pink noise. And we're going to do a bandpass filter. And we'll go back to using mousex.kr from, let's see, 200 to 5000. Yeah, there's always somebody who hears that wobble bass and ears just perk right up. So, okay, so now we've got this. This is a bandpass filter, and we're gonna show this thing here. And notice that there's sort of like a bell curve thing. That's because we have a band that we are allowing to pass, and we're attenuating things around that band. And our center frequency is in the post window down here. But BPF has a second argument. Well, technically a third argument. BPF, hello, there we go. An input signal, a center frequency. Look, there's all these warnings. Warning! Yeah, so again, values close to 0 may cause glitches and or extremely loud audio artifacts. This is a consequence of filters. Definitely digital filters, and analog filters can sort of go nuts on you as well. Analog filters can sometimes go into self-oscillation, which means they actually generate a tone with no input because the circuitry is just oscillating. Okay, and then, so the third argument is RQ. So some people might be familiar with the idea of a quality of a filter. Quality is the ratio of center frequency in hertz divided by bandwidth in hertz. Now, if we fix center frequency so that our band stays at one part of the spectrum, and then we vary the bandwidth, so if the bandwidth gets narrower, then center frequency divided by bandwidth becomes a larger value. So high quality filters, like with qualities of 20, 40, 80, those have narrow bands, and so they focus in. But in SuperCollider, the value we provide is the reciprocal of Q. So this is actually bandwidth divided by center frequency. You don't really have to think about the math too much. Just realize that values for RQ are between 0 and 1. They never go down to 0, but they can go up to 1. You should never set an RQ value higher than 1, and you should try not to set it too close to 0, because a reciprocal quality of 0 means that's like a dividing by 0 thing. It's like the bandwidth is infinitely small, and that's not something we want to do. So typically filters might have a quality ranging from 1 to 200 is not ridiculous, but 200 is kind of like, if you need a higher quality than 200, what are you doing? So that would be 1 divided by 200. So let's go ahead and add an RQ argument, and I'm going to say RQ var RQ equals mouse y.kr. We'll go from 0.01, which is 1 over 100, right? Max value 1, exponential, and we will poll this. Actually, well, yeah, we'll just poll this. It's fine. And then we'll shrink this back down. So at the top, we have a quality of 1, and the reciprocal quality is 1, right? The reciprocal of 1 is 1. So here's a bandpass filter with a center frequency that moves, and it has a quality of 1. And as I move the mouse down, the reciprocal quality gets closer and closer to 0, which means the quality gets higher and higher. So here's a quality of 2. Mouse Y is 0.5, right? There's quality of 4. In fact, we could just leave that alone and just say rq.reciprocal.poll. So we're just polling the reciprocal, but still using the value here. So, you know, this is our Q factor. So quality of 1, quality of 10. So it gets pretty quiet. Sometimes what I do is I will, the fourth argument of BPF is mul. And we know mul. Mul is everywhere. It's an amplitude scaling thing. So what we can do is multiply by rq.square root. And I find that the math here works out nicely. So if the quality you know, is 10, is this, I think this is right. So as we get lower and lower, let's see. No, we want to do 1 over RQ dot square root. So the quality square root. So if this is 1 over 10 or 0.1, then this is a value of 10 dot square root. And 10 dot square root is like 3.1. So we're scaling it up by a factor of 3 or something. So I find that this does a good job of compensating for the loss of amplitude from high qualities. So this should be notice how the peak amplitude does not change very much. So we're back to our theremin, but instead of a sine wave, we're filtering some noise. Yeah. Okay, so that's BPF. Band reject is very much the same arguments, except it rejects that band. Whoa, that's a little loud. Yeah, okay. This doesn't really work with band reject filters. Let's just stop that there, and we'll just multiply by 0.5. Notice how we have this notch, which is more visible when the quality is low. Because the quality is low, the bandwidth is wider, we can actually see a big notch being taken out of the spectrum. But with high quality, there aren't actually really enough pixels on the screen to see, or really hear. Yeah. Kind of a fun sound. Band reject filters, I think, are not really that useful for synthesis, but they are useful in acoustics for maybe like removing some very specific resonance from a room, or if you're in like a live sound situation and there's some feedback at some particular frequency, you can take a band reject filter and just sort of de-emphasize that one sound, that one frequency. Okay, so though that's LPF, HPF, BPF, BRF. Yeah, ringy snares, definitely. But it doesn't really do a whole lot with pick noise, just kind of makes it sound weird. Let's take a look real quick at RLPF. The R stands for resonant. So this is a low-pass filter that has a quality argument. And this is what tends to get used in a lot of the screaming wobble basses, because you can you can sort of create some resonant distortion and really emphasize the cutoff frequency as it sweeps up and down. So we'll do this, and all this seems fine, I think. We've got a resonant low-pass filter, frequency, RQ. We'll just turn it down real quick just to be safe. So with a low quality, it looks just like a regular low-pass filter that we already saw. But if we increase the quality, it sounds a lot more fun with like a sawtooth wave. So you can see on the scope that we kind of have a, let's see if I can finagle this. There we go. As we increase the resonance, you can see that the sawtooth starts to have this sort of sinusoidal shape to it, because the filter is bringing out that particular harmonic and emphasizing it. And you can actually hear the harmonics. Let's bring it all the way down to like 30. And then instead of mouse X, maybe we can do LF saw, 5, exp range, 40, 4000. It might be a little extreme. It's kind of, it's just at the sudden change at the end. Let's do LF try. Yeah, so those are resonant filters. There's RHPF. That's the same, except it's a resonant high-pass filter. And in the browse UGens filters, there's also BEQSuite. This has a lot of the same stuff, it's slightly different design. So bandpass, bandstop. There's also a high shelf filter, which will take a upper part of the spectrum and raise it up or down, and B low shelf, which takes a low region and raises that up or down. And peak EQ, that's a parametric filter, which is going to have a flat response, but a band it'll boost or attenuate it. So it's kind of like a bandpass filter, but bandpass filter just attenuates other stuff. A peak EQ. There's also one called mid EQ, which is another parametric filter. There's a lot of options here for filters. We're making progress here. So that's buffers and filters. I think there's just enough time to do maybe one last class of unit generators, and that's panners. So I think we can stick with what we have here. I might make this, slower and not quite so extreme. Maybe this will be nice. Let's just say keep the quality at 1/30. I want a low pass filter. That's what I wanted. Okay, so this is a stereo signal, as we can see. Let's make it a monophonic signal. Right, that's no good. It's just one channel now. But let's take a look at pan 2. And maybe some of you ran into this when you were coding your lawn sprinklers, and there was a bonus thing where you could try to get it to pan back and forth. So this is the key. Pan 2 expects 3 things: an input signal, that's sig, just like filters, right? It's something which processes a signal rather than generating a signal. so it needs to know what its input is. So that's sig a pan position. And we're going to initialize that to 0. Pan 2, if its second argument is 0, it pans it center. And if it's -1, it goes left. If it's +1, it goes hard right. And you can do any value in between positive and -1. And then we have an amplitude value, so it's just another mul value. For pan does not have an amp, mul and add for that matter. It just has, sorry, pan 2. Yeah, just input, pan position, and level. Very simple. So here, notice the sound is now a stereo signal, and it's pan center. But we can pan it left, so we'll say x.set pos -1. Right, and we'll slowly bring it center. I want more here. So yeah, bringing it center, and centered, and off it goes to the right side. So you can do something like -1, 0, 1 dot choose. Probably more interesting than that is to not declare the argument, but set it equal to a unit generator. So every 2 seconds, let's initialize the phase as 3 pi over 2, so it starts at -1. And SINOSC's default range is actually -1 to +1, so we don't actually need to modify its range. So this will go left to right and right to left. 1, 1000, 2, 1000. Right, there it goes. And of course, if you want a very specific trajectory of a sound in the stereo space, you can just make an nfgen. For example, let's have this go from hard left to hard right, back sort of almost, halfway between center and hard left, halfway between center and hard right. It'll center itself and then shoot off to the right again. So we'll have all of these be 1, 2, 3, 4, 5, 6, 1 second durations, right? Just and we'll do linear is fine because pan 2 is an equal power panner. So a linear pan from left to right is going to sound, like a perfectly smooth line because it uses this square root math. And we'll say, why not? Done action 2. There it goes, right? It's left, 1 second to the right, 1 second at -0.5, positive 0.5, and then at the end, shoots off to the right. You can make these a little bit longer. Let's just swap this out for a shaker sound. Oops, let's get this guy here. Shakers, pod rattle, sustain. So we're gonna read a buffer in, and instead of I think we can do away with this filter for now. We can just comment that out. We don't need that. We're just gonna say sig equals PlayBuf.ar. This is a monophonic signal, and we actually want it to stay monophonic because we're gonna pan it using pan 2. We'll just say b.bufnum and hard code that right in there. Done action 2. And I'm guessing this is going to be, well, actually, I'm not sure which one's going to be shorter. I guess we'll see. Yeah. Let's amp this up. Yeah, there you go. And, you know, if we want to be sort of interesting, we can say sig equals sig plus gverb, a little reverb action. Let's make a nice big room, nice long decay size, nice long reverb tail, rather, and multiply this by something small. Yeah, I don't want done action 2. Let's just take that away. And let's make an extra. How are we going to do this? Oh, you know, we're just going to temporarily take away done action 2, even though that's not the right thing to do. Just want us to be able to hear the reverb. Yeah. The problem here is that this synth is now just living here, even though it's not doing anything. It's actually outputting a little bit of a DC offset. That's because we got to the end of the buffer, which, you know, is maybe a non-zero value, and there we go. So let's actually go ahead and command period that. So other panners, there's balance 2. This is like a panner, but it's for a stereo signal. So when you pan a mono signal, you sort of pan it hard left, so it's only going to the left channel, only to the right, but it's the same signal. With balance 2, like if we do, if we had a stereo buffer, you know, with like totally different sounds in the left and the right, as we use balance 2 to, you know, we input the left signal, the right signal, and the pan position, it's going to favor the left signal with a value of -1 and favor the right signal with a value of +1. Let's do that real quick. Just make a brand new function here. Sig equals the array sign osc.ar. Let's say 500. And it's a comma there, saw.ar. Let's do lf try 100. Okay, so here's our stereo signal. Right, sine wave on the left, triangle wave on the right. And if we say sig equals balance 2, oops. Now we want to give it the left signal and the right signal, but we actually have these together in one variable. So what we can just say is sig at 0, sig at 1, and let's do lftry.kr. And this is going to be a triangle wave panner, so it's going to pan left, right, and that's all we need. So instead of actually panning a signal by moving it in the stereo space, here we're just amplifying and attenuating 2 signals, which are being sent to the left and to the right. Okay, my neck is starting to hurt, and it's 9:45, so I'm going to wrap up. There's kind of a lot of stuff to throw at you, but I'm hoping that everyone's sort of getting to a place where, as long as you know that a unit generator exists, you sort of have the skill and vocabulary to read the help file and get a general sense of how it works and be able to implement it in just a, you know, a synthesis function in some way. There's another panner, pan AZ. This is an azimuth panner that pans circularly through an equidistantly spaced speaker ring. So it can be any number of channels, 4, 8, 16, you know, anything like that. And it's pretty useful. It's also, I was thinking maybe we'd get to like some of the delay lines in this video, but you know, I guess not. It's a lot of stuff to cover in just 2 hours, but delay is sort of fun, just to create echoes, basically. There's multi-tap delay. There's comb filters, which is a delay line with feedback. There's all-pass filters for, oops, it's lowercase p, or which is like sort of like comb filters, but the algorithm is different. Sort of has a coefficient to reduce resonance, useful for reverbs. Okay, so yeah, if anyone's got questions, you can ask them now. You can maybe paste them in some code. I can take a look at it real quick. Or you can leave a comment on the video when I upload it to YouTube. All right, so I'm going to cook up some in-class problems involving some of these new UGens tonight, maybe tomorrow. And I'll see everybody taking my class, in class tomorrow, for another round of in-class problems. And yeah, thanks everybody for watching. I hope this was useful. Glad I didn't blow anyone's ears up with my filter demonstration, but it's just important to know that filters are dangerous tools. Okay, so I guess that's it for me. Thank you all for watching, and have a good night.